Hello everyone, my name is Inga and I'm pleased to welcome you to the webinar Building Advanced Expressions. It will demonstrate how to build complex structured expressions. Our presenter today is a long-time NoMagic employee, Tomas Juknevicius. As a senior systems analyst, Tomas has an extensive knowledge of various MagicDraw functionalities, UML modeling, and profile building. Being a father of structured expressions functionality, he is a go-to person when learning to build and use complex expressions. Tomas holds a Master of Science degree in Computer Science and is an OMG certified UML professional. Before Tomas starts, let me remind you that today's presentation and demo will take about 50 minutes and the question-answer section about 10. If you have any questions, you don't need to wait for the question-answer section to ask them. You can do this during the entire session, and Tomas will answer them later on. Just type your questions in the questions area. Due to limited time, some questions might be left unanswered. In such case, answers will be published later on the webinar's webpage. Please note that the webinar is being recorded. All the registrants will be provided with a link to the webinar's video on YouTube by the end of the next week. So, Tomas, are you ready to start?
Yes. So without much further ado, let's start our session, because we have quite a lot of ground to cover, and I'm not sure if we'll fit everything into that 55 minutes which we have allocated. Okay, so the topic of today's presentation is structured expressions, and in particular more complex cases of them. So if you have ever made a smart package, or if you have ever made a derived property, or in the dependency matrix you specified criteria, you are probably a little bit familiar already with this dialog in here. So but you are probably more familiar with the simple or standard look of that, and only not a lot of people can delve into depths of that and employ it to specify more complicated cases. But we'll try to remedy that with this seminar. So now, first of all, why do we need these things? So basically, we need these structured expressions for the complex analysis functions. So modeling tools live and die by the strength of their analysis functions that they provide. Think about it. So why do we model at all? So we model because we want to get some insights on that model. So if the tool is just a modeling tool, meaning for creation models and displaying of models in the diagrams, that's all good. So you can get insights looking into those diagrams. But also, tool can calculate something for use to provide some more complex analysis cases. And during the time MagicDraw has grown, and it employed a lot of these active, so to speak, active features of MagicDraw. So wherever something is calculated, something is shown which is not a direct model information, but some derived modeling information. So as I've already mentioned, derived properties, custom table columns, relationship criteria in the matrices, dependency relation maps, relation criteria in relation maps, smart packages, so active legends, for example. So this is a new feature which we'll have in 19.0 upcoming. They also model metrics, and sometimes model validation can also employ these calculations. Now, to do a calculation, you need to specify that. So in MagicDraw, you do that with this structured expression dialog. And okay, we'll delve into that. So a couple of notes. So we will not be covering concrete applications of the structured expressions. So basically, where you employ them, it's up to you. So we'll be covering just a computation itself, and of course a little bit like it will create a couple of smart packages and a couple of derived properties, but just for sake of example. Now we did have an introductory webinar for very simple cases of the structured expression. So my colleague Aurelius has already done such a demo. So if you have missed that, you can follow this YouTube link. And to see if you are not familiar, for example, with like simple cases like a simple navigation or simple meta-chain navigation, stuff like that. We'll be doing more serious computations now. And some of the features demonstrated will be from 19.0 upcoming, but I'll mention which of those are there. And so it's not a lot, but okay, they are nice, and I can catch an opportunity to like advertise them here. Okay, so first a little bit of abstraction. So what is an expression tree? So let's say we have jump into math world and see. Let's say we need to compute like this mathematical expressions with two given variables in there. So x is this and a is that. So we can plug that naturally. We can pull out our calculators, plug those values in, and get to the answer 18.1. 1.8. sorry. But how did we do that? So we did that by following what is called an expression tree. So we first start with the primitive values which we have, so the pi and the 2. We plug those into division operation. We specify plug the value for x, plug the result of that and the previous division into some operation. Again, get a sinus of that and multiply by a. And this thing is called an expression tree. So it's basically a tree of the operations which have several inputs and one output, and the leaves are usually, so there are two types of leaves. So either it's constants, so as pi or 2, and what is called either environment variables or simple variables or contextual variables. So x and a, so the things that are coming from the outside. And this is like an expression tree in general. Now let's see how so in MagicDraw, so when you're constructing structured expression, again, you build that structured expression tree in the same manner, out of starting with the simple constants, invoking some predefined operations and plugging the inputs, outputs of one operation into inputs of the other operation. We can chain those functions to compute something. Now the contextual variable, so expression, as previously mentioned, never lives like alone, because if everything is constant, then you can calculate expression once and like give one fixed answer and don't bother with it. But we usually want that expression to be calculated for a different, so for example, we want a derived property calculated for each element of a particular type, or we want to apply the relationship criteria for each row in the dependency matrix. We do multiple calculations, and into our expression we feed as a parameter. Usually it is a particular model element. So what we had in this expression as these contextual variables x and a, in MagicDraw there is a contextual variable called this. So whenever you're doing, as I said, derived properties or relationship criteria or the smart package or custom column, your expression we'll have a contextual variable called this, and during the invocation, MagicDraw will feed a particular model element into your expression, and your expression will calculate based on that element. And so let's not overcomplicate things and start with a very simple demo. For example, let's grab our standard coffee machine sample in here, and let's create a smart package which calculates all requirements. So we go into expression, we jump into our expression building window, and since we are now all experts, let's switch to the expert mode and specify that we want to, let's say, find all the requirements in our project. So let's say we say that this is a requirements. So we can specify the scope. So for example, either entire model or let's say just a particular package, and we can run that. So finish our query and see what the results are. So this is very basic, but what I want to illustrate to you is the shape of our expression tree. So we specified this nicely here in the GUI, but actually beneath the scenes, what we can see in here is that we have an invocation of the find operation, which is a predefined operation in a structured expression. And this find operation has a lot of parameters. So each of these elements in here are simple parameters. Some of them, like these are here booleans, some are textual. There are a couple of more complex parameters, for example, collections, and the search string is a string. So basically what we have in here is an expression tree of one invocation of the find, feeding to it parameters which are predefined. This is very simple, but in theory you could feed all these values into our find, not make them not constant, but calculate them somehow. So for example, you could, let's say, make a smart package which searches for strings that are of the same name as a smart package is. So for example, all elements starting with A, or all elements starting with B. So for example, to make some index, you could feed in here, so into this parameter of the find, not a constant. So the constants are here. So previously we had it like that, which is what GUI created for us. But you could feed a value of some calculation, and that would be so your find will then be computing some, not a fixed query, but something more complicated, or so to speak, more dynamic. Let me give you some example in here. So I want to show how operations are connected. So if let's say we have a bunch of requirements there in our model in here, but we do have those requirements are connected with dependencies to some other model elements. And we just want to write such a query which pulls all the requirements and then pulls all the dependent elements on those requirements. So I do have an example here predefined. So let me. So this is the meta chain. So sorry. we do have an expression tree here of this form. So there is a operation find operation with particular parameters, again as we've seen before, requirement pulling all requirements, and then we are feeding those requirements into the meta chain navigation operation. So if you have watched that previous video, Aurelius, how you normally use meta chain navigation, for example, from when you make a derived property, which is meta chain navigation from particular element by some criteria. In that simple mode, you just place the meta chain navigation, and your input into meta chain navigation is usually this contextual element, this, and then you navigate from that. But that is how to say, simple for the simple cases. For in our example here, we are feeding meta chain navigation not the contextual element, but the results of our find. So according to this expression tree, MagicDraw will find all the requirements in there and then do 2 steps of meta chain navigation, basically from the requirement to the attached dependencies where the requirement is at the supplier, and then navigate to the dependencies client. And once you specify such an expression, let's see what happens. So what we have here is a bunch of the activities in our coffee machine sample. And now if we look at each of these activities, among the relationships, we should see, so here they are. So this particular activity does have the relationships to 2 requirements in there. So our computation did pull out those depending activities in here. So this is just a simple, as I said, building a simple expression tree, so like feeding results of the one operation into computation of another operation. So now I'll have to touch a little bit of the pitfalls in here and some nice things, or how to do things in here. If you have always used simple navigation, you always see these 4 nodes. So basically, the expression building dialog tries to like sit on two chairs simultaneously. It wants to be both simple for non-advanced users and provide advanced capabilities for advanced users. So these 4 nodes are always shown in the structured expression tree. They are basically for non-sophisticated users, so that they always can start with a particular node. So if you're just like making a simple relationship criteria, you can these 4 nodes will be pre-created for you by the GUI, but for our computations, you need to know that until you input any, for example, specify any criterion on simple navigation, or until you specify parameters for the find, those nodes are not, how to say, they are not active, so we are not computing anything. So in reality, this should be a proper view of our expression tree. So just removing the clutter. So if we are calling ourselves advanced users, so we can, like just for the sake of clarity, when we are doing our expressions, and those expressions are sometimes rather large, just remove the nodes which are not needed at the moment, so that they are not get in the way. So this is a little bit of a problem. So these additional nodes, but they are for non-advanced users, so that they always have something to start with. Now for us, meaning more advanced users, we want to have, so I want to point out or give some tips of how to build these trees. And this is a basic tree manipulation, meaning that in this tree you can drag and drop nodes. So for example, it's rather complicated to build expression first time and starting from scratch. So you usually build it piece by piece by like starting with a small step, modifying it, and so on. So what I want to show you is how to manipulate these expressions. So these nodes in here, you can drag and drop them, and for example, to combine the meta chain with the find, you can let's say you start with the find. And from 18.5, we have this nice evaluation mode. You very quickly evaluate your expression, see, aha, these are the requirements which I need. So now I need a meta chain. So I make a meta chain from those and drop my find. Oops, missed it. Drop my find as an input to that meta chain. And again, starting with actually, if we name the element, let's see, supplier dependency. Again, we made one step of a meta chain. We can run evaluation, see if interesting. Okay, let me try again. Okay, meta chain. Okay, requirements. Yeah, so starting from this thing. So let's say we want to evaluate that. So this is rather strange. It actually should have made me a list of dependencies in there. So I wanted to show you that you can incrementally build your meta chain step by step. I'm wondering what went wrong in there. Okay. Okay. Anyways, so after you. So you, as I said, you build your expression by dragging your nodes and dropping into other nodes, or sometimes, for example, for a particularly used operations. Let's say we want to do we did our computation and we want to further filter it. There is this dialog in here. So, for example, we can say we want this node to be an input collection of a new filter. And what MagicDraw does is restructure you this expression tree and basically drops you your meta chain element as a particular input of that operation. So these are for the most commonly used nodes. Another tip. So okay, let me see what other tips do we have in here. Okay, drag and drop, copy paste. Okay, another tip would be to use, so basically in these expressions, again, it is very useful to name your nodes appropriately. So let's say MagicDraw makes you an operation name according to that operation, what it does, but you can always like specify a better name for that to reflect the reflect in more details what you are computing here. So here I can say find all requirements. Okay, and now in here, instead of simple like a nondescript meta chain navigation, I can say pull all dependent elements. Okay, and now our expression tree is much more verbose, and so if you look into this expression after 2 months, you can read what it does instead of rummaging into those expression nodes and trying to guess. Okay, so this is okay. We covered those things. I want to touch one more thing. So we have we did trial expression evaluation from the specification window. You can also use an expression evaluation dialog in here. So basically, it's the same window for if you are building an expression, you can, or let's say you are debugging an expression. Let's say you want, so something is wrong with your current expression, you can go to edit and copy, and your expression tree will be copied. And now if I jump into this other dialog in here, and I can say edit and paste whole, and I do have my expression in here, and I can manipulate in it or evaluate it in parts and so on to see what's wrong with it. So this is rather neat dialog. We have introduced that quite recently in 18.5. I'm not sure if it was already in 18.4, but it's a recent add-on. Okay, let's jump in here. Aha, so we actually we have run through the we already seen a simple like a meta chain operations in there. So let me give you more, how to say, more formal details. So what the meta chain operation does. So meta chain operation has one input, which can be either a single model element or a collection of model elements, and for each step which you specify in the meta chain, this operation does the following. It takes all a collection of the inputs, filters that collection according to the type of the step. So let me jump back into my meta chain in here. So it takes a collection of inputs. Then for each step, it filters of collection of elements by specified meta class or stereotype, so by type. So in this case, we are specifying we are only interested of requirements, and then navigates to a particular UML property or a tag, in this case, supplier dependency. And it gets another collection there, and then the step repeats. Again, that collection is filtered by the dependency type in there, and we're going to client of that dependency. So suppose you have some requirement in there, and you should be able to see here supplier dependency. So this meta property is that meta chain navigates, and it does it for each of the elements in the input collection, and for each. So the next step would be of that dependency go to the client. So this is how this is what this meta chain expression does for each element. So now, because meta chain operation can take collection of inputs, this means that it is, how to say, symmetrical. So basically, it takes a collection and it gives a collection. This means that you can also, whenever you have an expression of multiple steps, and let's say you want to insert some filtering step at some point of a meta chain, you can always do that by rearranging your expression. So okay, let's say we also have a we have our meta chain in here, and I want to, let's say, navigate to supplier dependency of the requirement, but then I do want to calculate some complicated filtering. So basically to filter those dependencies by some complex criterion in there. So what I can do is always I can split this meta chain, and so let me do it like that, and make this. So basically, what I'm doing here, I'm doing find, and then instead of just a single meta chain, I do have one meta chain doing the first step and another meta chain doing another step. And now I can insert in here, for example, a filtering step. So like that. So now I would have a find, then navigate to the dependencies, then do some filtering. I would need to specify a condition in there. We'll not do that due to a shortage of time. And then you would navigate the second step of that meta chain. So this is, how to say, very nice. So let's say you have like a 5 steps of a meta chain, and you want to insert some filtering criteria after the third step. You do as I did here, basically chaining the meta chains, and insert a filter in the interim step. Okay, so now as it is out of the box, the structured expression dialog only allows you to use some predefined set of operations. Actually, we can look into them again in here if I remove everything. Here is like a predefined set of operations. We do have simple navigation, meta chain, find, with a couple of them here, but you can also make up predefined operations in the model and reuse them in different, so in several other structured expressions. So you could have an operation library somewhere in your model, and you can call those operations from everywhere. So if you, let's say, fix a bug in that operation or modify that operation slightly, you don't need to run through all your model places to modify some computation everywhere. Your computations will be updated, and also you can create new operations from scratch. We'll see how to do it with the scripts, but for now, just for the sake of brevity, let's say we want to do a simple simple operation of the set intersection. So if you see, MagicDraw does have predefined union and exclude operations. So these are set operations. So union is a union of sets. Exclude is a removal of one set from the other. But sometimes you need, for example, set intersection. And there is no predefined operation for that, but we can very easily define it for ourselves in terms of the exclude operation, which exists. So let me show you how to do that. So just for the sake of order, let's make a package for them. Operation library. And to make a reusable operation, you create your model element of opaque behavior. So create opaque behavior. Let's make it set intersection. Now what you need to do is you need to specify the parameters. So the parameters for these operations can have multiple parameters. So not just like a simple expression only has this one single contextual variable this, but your operations can have several parameters. So let me create a parameter, let's say x, and parameter y, and we'll be calculating the intersection of those. Now comes to a couple of very important things is setting the type of your input parameters. So usually you do have operations which either operate on primitives, on model. So most complex case, most common case is operating on model elements. So you would set your type of a parameter to either abstract model meta class element, or if you know that your operation operates on something more concrete like a class, you can set it in here. But for this intersection operation, so basically it doesn't care what type of items are there. So it can operate on both model elements, and it can operate on primitive values such as numbers or strings, or it actually can operate on objects of on any kind of Java object which can be inside of a MagicDraw. So because of that, we do want to specify use a special predefined type. So in our library, we do have this Java lang object, which is for if you know Java is the rootmost class of the class hierarchy. So basically, it can be anything. So we say that our X accepts any type of model element, and one more thing we do want in here is we want to specify multiplicity. So if you just specify the type, just such as element or integer, that would be a single element. But now if you specify that multiplicity is many, this means a collection of things. And with that also comes two more flags. So basically you can leave it like that, but there is a couple of more flags if you want a more specific collection. So we do have, so this comes from the from UML. Basically we are interested in is unique and is ordered flags. So if your parameter type specifies that it's multiple parameter, meaning multiplicity is many, and is unique is true and is ordered is false, this means a set, meaning that non-duplicate elements with unknown order. If you specify is ordered and not unique, then this is a list, meaning ordered elements which can have duplicates. Neither unique nor ordered, this is nondescript, and also a rare case is for both unique and ordered. So this is ordered set. So, but for our case, we are computing intersection, so we'll do just is unique. So meaning that we are operating on sets. Okay, so this is an X and this is a Y. Let's do it again. Lang object, multiplicity. Okay, so now we do have two parameters, and now we specify body and language of our operation, and you can actually specify this body and language in several different ways. So basically, we'll have in our later in our demo a little bit of scripting. So you could, for example, choose a JavaScript and write your operation in JavaScript. You could use Python, Ruby, so any of these built-in scripting languages. There is also an option for binary. So if your company does have so Java leaning, so Java developers, you can write a MagicDraw plugin and implement some particular computation operation in Java, which does some complicated thing in there, and compile that, make a plugin for MagicDraw, and you specify your expression class name in here, and this would be that your expression would be called. But for our case, let's use again structured in expression, and what we want to do is use an exclude operation twice. So and now, so this is important. So previously we operated only on this, but now in our reusable operation we need different contextual variables. So I will say that I'm excluding from the X, and what is excluded is another. So this is a trick from the set operations. We can implement the intersection with the two excludes. So basically, I'm excluding from X that which is exclusion from X of the Y, and so this is my operation. Now to test that, I could use some smart package, employ that into smart package or in some derived property, but due to shortage of time, I'll just show you how to call it from this dialog, so directly to just to test it out. So let's jump into our operation library, pick our intersection, and let's build two sets. So okay, two sets, and now first set will be of a couple of model elements in there. So okay, let's pick a couple of requirements in there, just for the sake of this one. And now another collection will contain two again, very quickly. Okay, so there are two collections, and their intersection should be single model element. Now, with the fingers crossed, let's do that. Okay, and now we see that our computation is performed. So now we would be able, for example, to employ this intersect operation in our expressions, as I said, in smart packages of derived properties and so on. So now turning to using scripts. So I've touched a little bit of the scripting. You can do it two ways. Either make a reusable operation, meaning, as I did in here, an operation for sorry, to be used in other structured expressions, or you can embed your scripts directly into other structured expressions. We'll have that later in the demo if I do have time. Sorry, I'm running. I'm very late. So let's say you want to go the first route and you want to specify an operation in some script. From JavaScript you can, and actually from other scripting languages, you can actually access all MagicDraw model, all Java API, and also you can access other MagicDraw objects which are not model elements, but they are in MagicDraw API. So for example, if you have a diagram, you can specify, so you can find out using MagicDraw Open APIs what elements are depicted in those diagrams. So this information is graphical information, and you usually do not have it accessible in like these simple meta chains or simply from the specification windows. But with the help of scripting, you can access those things. So just for the sake of brevity, let me make a scripted expression, for example, to calculate size of the collection. Okay, let me have a size in here, and okay, the size would only need one parameter in there, and let me use JavaScript, and so now I can say x.size. Sorry, and to know what you can call and not or not as I've said, you can look it up on Java API. So Java documentation is publicly available in Oracle shares everything. So when working on collections, you have Java util collection, and we are calling in particularly this method in there. Similarly, MagicDraw does have Open API published. So if you install your MagicDraw somewhere, you go to Open API docs, and there is a Java doc there in there. You can look into those classes in there and see what you can do with the particular objects. Okay, very quickly let's run. Okay, we do have size of x, and now again let's have an expression evaluation. Instead of intersect, I do have okay, size. So I'm reusing the same operation for the quick test. Okay, so now I have a size called on the collection of the two objects, so the result should be 2. So now we see that it's really 2. So, or for example, the very commonly used operation is testing if a collection is empty. Again, something like that. Again, you would want to call is empty, and you would have a test, so Boolean test for whether some particular collection has something or not. Such a test, so is empty test, is very useful for filtering some conditions. Let's say you can have collect your collect some behavior, some model elements, and filter them by the condition that there are no outgoing dependencies from them. So basically, elements like not connected to anything with dependencies. So you would use a meta chain to gather your dependencies, and then you would test if that collection of the dependencies is empty for each element, and that would be a simple way to filter those. Okay. Available. Okay, MagicDraw APIs, including okay, so I do want to show you also that it's possible to access non-model elements. I do have an example in there for the diagram. So the depicted elements of the diagram. It is a little bit nasty script in there, but it does operate on MagicDraw API. So if you, for example, have a project, you can get get the diagrams in that, and get the presentation elements, iterate those, and pick all the model elements that are depicted in there. So this is, by the way, the case where the script is not in the reusable operation in the model, but embedded directly inside the structured expression. So instead of operation from model, you would use a script and pick your scripting language and put a code in there to access some particulars of MagicDraw. And once you have such a derived property in here defined, you could, for example, jump into your diagram and see if does it show directly. Okay, so here you have a direct custom built derived property which shows what model elements are depicted in the diagram. And again, once you have that, you can filter or navigate from those elements. So, for example, get directly depicted elements, and from them navigate to something else by chaining those operations in there. Okay, so we did have these things. Okay, horribly out of time. So I think we'll burn through the question time, because we do have a couple of very important concepts to cover, and these are higher order operations. So this is complicated stuff already. So let's think about filter operations. So usually you do need to filter by filter various collections by various conditions. So filters by some property value, filter by existence or non-existence of the relationships, as I mentioned before, filter this, filter that, filter by element type, and so on. And it's not possible to make a lot of filter operations for each case. Because of that, the usual approach is to make a single filter operation, which does which takes as a parameter a set of elements, and then it takes a second parameter of the filter operation is special. It doesn't take a value, meaning not some number, not some model element, not a collection of model elements, but it takes a filtering criterion operation itself. So in contrast with this our expression tree where I said we fill when expression is evaluated, first the leaf is evaluated and then it's fed to to a higher operation as a value. So the higher order operation parameters, such as filter second parameter, is not evaluated in itself, but that operation is passed as an object inside the filter, and then filter calls that filtering criterion operation multiple times, and however that argument is used is at the discretion of the filter operation. So if we use analogies, you could make an analogy that we do have a drill and there are various kinds of drill bits, and if you put one drill bit, you can drill, you put another bit, you can tap, you put the third bit, you can screw and unscrew things. So in the same kind, the filter operation does take a condition, and according to that condition, filters the incoming collection by some criterion. Again, we are horribly running out of time, but let me very quickly demonstrate that. Okay, let's say I have a structured expression, and I want to again a requirement. Let's say I do want requirements in there in the whole project, and okay, for just for this case, I'm using evaluate. All right. So what I have done in here, I basically again found all the requirements which are in the model, and then I fed that collection to a filter, and this condition here is another operation which filter will call. So currently I do have it set to true in here, meaning that this condition is always true, and filter doesn't filter anything. But let's say now I do want to filter those requirements which do not have the incoming dependency relationships. So I would use my isEmpty operation, and we'll use a meta chain. And again, this is the tricky part. You need, so basically this nested operation has its own parameters. For the find, it's a single parameter, and here I have R, and I need to specify that I'm navigating from this R parameter, not from this, which is that value in here. So I do want to, okay, let's see, requirement supplier dependency. So this would so this find would find me all the requirements, and filter would iterate for each requirement and call this operation and pass each requirement in here. So in that condition body, we would navigate to the supplier dependencies, meaning incoming dependencies for our requirement, and then we only want those requirements where the set of dependencies is empty. So let us try to evaluate that. And here we see our list is shorter now. So now with such an expression, I do have requirements which don't have any incoming dependencies. So this is for example requirements which are not covered, so not satisfied by any block. So this is how you can do filtering. So basically you can specify your operation with a nested operation and structured expression in the body. As an alternative, you could write a script in here. Again, you would pick a scripting language which you're most familiar with and write your condition in here if your condition is easier implemented with scripting. Or you could use again some operation from model if you do have an operation which does exactly what you need in here. All right. So again, due to shortage of time, let me very quickly run through other. So there are other higher order operations, in particular a map operation, which you want to use when you have a, for example, some collection of elements, and you have a you want to apply a particular function on all of them. So, for example, let's say you have a bunch of blocks, and you want to, and each of block has some weight, which would be a custom tag. You could, so the map operation would get a collection of blocks, and if you specify that for each block I want to take this weight tag value, output of a map operation would be a bunch of weights. So currently this operation is not available in MagicDraw, but we do have it in Cameo Collaborator, so our other for free product. So you can if you install that product, you can basically steal it from there, or either copy into your project, or just attach that Cameo Collaborator project and use it as is. So I do have it attached to this particular model in there, and there is here in the helper operations, so the map operation in there. There are other goodies in here if you do want to use them, such as or not. So our is empty operation, which I implemented as a script for the didactic reasons, is here implemented in Java also. Ands, contains operations. So there are a bunch of goodies in that Cameo Collaborator library, and you can basically copy those operations into your model and use them, or just attach that project and use them as is. There is okay. So again, really running out of time now. So there are other. So you can also roll your own higher order operations. So the ones which are not defined by MagicDraw, and so for example. Again, so you make a higher order operation just the same way as you do a normal operation. So basically, you make an opaque behavior, and the only thing different is that when you specify the parameters, which are which are special, so the same as a find condition, filter condition, you use a special built-in type. So in here, for example, so this is the built-in type which you need to use. So I do have an example here for the zip operation, meaning having two collections, iterate through both of them, and join them with a particular, by calling some particular operation. For example, you can multiply two lists, so first value of the first list by the first value of the second list. So this is just in this example, just a bunch of a script. But we will be in 19.0 when we are releasing that. We'll be incorporating many of these things which I'm demonstrating, like is empty or count or this zip or reduce operation inside MagicDraw, so predefined. So you will not need to code them in script, but if necessary, for example, if you invent some other higher order operation which needs to do something similar, you can do that by the way of a scripting. So for example, again, we do have a reduce operation in here, again implemented. So basically this is for if you have a bunch of numbers and you want to sum them all or multiply them all or do some combining into a single value. So basically the reduce operation takes a list, takes an operation which does that combination, which can be, as I said, in some cases it can be sum if you do want to sum, or multiply if you do multiplication, or some other more complicated combinator, and then initial value, and basically it iterates through your list and combines the initial value with the first element, then the result with the second element, and so on and so on. So for the sum, we would specify fold operation a plus b scripting, so simple sum. Initial value we will specify as 0, and with a reduce, I could have a summation of all the elements in my in my collection. So let me very quickly jump to the last demo to tie something into some meaningful computation in there. So let's say we have let's say we have our system model in there, which consists of some bunch of blocks in there, and each, so in this case I do have a car model, so rudimentary car model, and each block has its own mass, and then it has parts which have mass in turn. So, and our task is to calculate the composite mass of all this subparts, subparts, and so on and so on. And what's more, if some part is multiple, like here we have 4 doors, or here we have 4 wheels, we need to multiply this thing, the mass of the wheel by the multiplicity of my part, and use that as an input to my block. And so I do have a specific derived property for that, and let me show you that it calculates things. So let's see the mass of my car. So what would be the mass of my car? So you see a cumulative mass is 2020, so that would be 4 doors of 50 combined with the body, so 200, 1,000, 1,300, 1,800, and 1,920, and 2,020. So basically it does calculate the things which we need, but let me very quickly show you how it's implemented. So basically I have created a custom operation which, given a block, finds this number in there. It's not very trivial to find, because you need to okay, let me jump into my expression in there. So you need to basically navigate to all the properties, so basically all the attributes of my block, and then so basically I do want to find the property which has a particular name, and then fetch the default value again of that thing. And here is a simple adapter, basically taking first value of the collection. So basically I would, for each block, I would grab this particular value of the self mass. So if you try to invoke that thing, for example, get mass, and for let's say, okay, I will put this as a contextual variable, and let's say self mass of the body, and we do have a number which is in there. So this thing works, and now having that, we need to compute a derived property which would be quite a complicated one. Again, let me very quickly run through that. So I need to sum all, meaning call the reduce function, which I mentioned before. As I said, my fold of the reduce is x plus y, meaning that I'm using summation. I'm starting with the self mass of the current block. So that would be like a mass of a car, mass of a body itself. And then I'm adding that to the masses of the parts. So the masses of the parts would be again, get the parts, which is just an owned attribute, and apply the map operation, meaning for each part, I want to compute something. And that computation would be to multiply. So here is the embedded script, again, doing just a multiplication. And I want a cumulative mass of my attribute, meaning, or of my part, meaning I need to go to the type and get a cumulative mass of that type. And then I need to get multiplicity of my part. So the property upper value is multiplicity of that. So here I'm getting all the parts, applying this mapping operation, which extracts basically multiplies for each part its cumulative mass with its multiplicity. So I would have masses of the parts in there in this list multiplied by their multiplicity. So if you have like 5 wheels or 3 wheels, your mass would change. And then I am summing those numbers with the fold operation to arrive at a cumulative number. So as you can see, this is a recursive definition, meaning that the cumulative mass derived property is looking into the cumulative mass of the children, and those children looking into cumulative masses of the children, and so on. But this is doable. So as we can see, so and if, for example, you let's say you have just your car just has 3 wheels. You should be able to, if you recalculate, yeah, your car should have a. Okay, so now you can see that the mass has changed. So from 2020 to it decreased by 30. So this is basically the end of my demo. So unfortunately, we will not be answering questions online because we are already 5 minutes over time. But just as a conclusion, so basically the structured expression tree is basically we have fallen to Greenspan's 10th rule, which is a jocular rule saying that any sufficiently complicated program contains an informally specified book-ridden slow implementation of half of common Lisp. So basically, structured expressions in MagicDraw is some application of functional programming style to build an expression as a tree of a function. So basically, whoever knows the functional programming, they should be familiar with these like higher order operations and stuff like that. But on more serious notes, the structured expression allows you to build rather complicated computations by gluing together simpler blocks in the manner of like Legos. So in Legos you do have a predefined set of the blocks, or also you have some specialty blocks maybe for those special occasions, and you aggregate those, put them together into something bigger and more complicated and nicer and so on. So okay, and with that, let me finish my overtime demo again.
Thank you, Thomas, for the presentation and demo. And since we have no time for questions, let me thank you again for participating. We hope to see you again in upcoming webinars. And if there is anything else you would like to ask, please don't hesitate to contact us. Goodbye.